Let's begin. So, hello, I'm Liam Wright. I'm a lecturer in statistics and survey methodology at the Centre for Longitudinal Studies at University College London. I'll be presenting a webinar today on handling survey mode effects in the UK cohort studies. I'll be presenting with Georgia Tomova and Richard Silverwood. Georgia and Richard, do you mind just introducing yourselves, please?
Thank you. So, hi, I'm Richard Silverwood. I'm an associate professor of statistics and the chief statistician at the Centre for Longitudinal Studies.
Thanks. And hi, I'm Georgia Tomova. I'm a research fellow in statistics and quantitative social science at also the Centre for Longitudinal Studies.
Okay, so what is a mixed mode survey design? Well, there's some background. Each new communication medium typically produces a new way to conduct surveys, which academics like to exploit. So we've started with face-to-face interviews, then there's postal questionnaires, telephone interviews, then with the advent of the internet, web questionnaires, and with software like Teams and Zoom, there's now surveys being completed with video interviews. Surveys don't necessarily use just one mode. They can use multiple modes in a sweep or between sweeps, and surveys differ in how they might mix modes. They might combine face-to-face interview with postal questionnaire, telephone with web questionnaire, for example. This mixing of mode can occur within a sweep. So given a set of participants, some might answer by telephone, some might answer by web questionnaire, or it can occur in longitudinal studies or repeat cross-sectional studies between survey collection, data collection. So for instance, in NCDS, you had people, I think, answer by telephone at age 46, and then at age 50 it was face-to-face. So individuals differ in how they respond to the survey across time. Surveys also differ in how participants are assigned to mode. You might find a mixed mode survey design where people are offered a choice of modes and they can select that themselves. Or another popular example is the sequential mixed mode design, where people might be pushed to one mode, and if they don't answer to that, they then are offered other modes that they should hopefully respond to. So, for instance, next steps use a sequential mixed mode design where people are initially offered web questionnaire, followed by telephone survey, followed by face-to-face. Now, there's benefits of mixing modes, but there's also costs. The benefits are that it's cheaper to run. You can push people towards the cheapest mode to begin with, and so you can get, if you've got a finite amount of money, you can get more sample for your book. Another benefit is that you potentially have higher response rates. If you offer people a set of modes and some are more convenient than others, then people might be more likely to respond in those more convenient modes, whereas they might have just not answered at all if you just offered the less convenient mode. A sort of side effect of having high response rate is that potentially you'll have more diverse samples, and these might also be more representative. So in political polling that has relied on particular technologies to find out people's voting intentions, they've had problems. For instance, if you rely on telephone, you'll get a certain section of society answering telephone surveys, and that might not be representative of the full population. The issue with mixing modes, though, is that how items are measured can differ between modes, and we'll talk more about this throughout this webinar. But the side effect of this is that it can cause bias in analyses. So I'm just going to quickly show an example survey item. This is an item on self-rated health, which has been asked in one of our, well, it's asked in all of the cohorts, but it's been asked in the 1958 birth cohort study, which is the NCDS, since they were about at age 20, I think, and it's been asked in different modes. So at age 55, NCDS participants, the sweep used a mixed mode design where people answered by telephone or web interview. By telephone, you would be asked this question on how is your health overall by an interviewer over the phone, and your response wouldn't be anonymous. You'd have to give a verbal answer, and you'd hear the question as it be read out to you. In the web interview, you would instead read this question, and no one would be able to see or hear your response potentially. So these two modes differ importantly on whether they're anonymous or not, and that could influence people's responses, because people might be less willing to reveal that they're in poor health if they actually have to say that to someone, and that will affect the response that's given. So how can this mode affect, differences between responses between modes and due to measurement are called mode effects. Due to how items are measured are called mode effects. So how can this bias type, this can bias all types of analysis. So firstly, thinking about this descriptively, we'll just continue with this self-rated health question. So if you had a telephone-only survey, you might get a different response and a different sense of how poor health was in the population than if you'd used an anonymous survey. Longitudinally, if you moved from a web survey to a telephone survey, it would appear potentially that health was increasing, but that's actually just a spurious epiphenomenon of changing modes towards one where people are more likely to give socially desirable answers. It can also influence correlations. So this can occur where you're looking at the association between two survey items that are both subject to mode effects, but it can also occur where you're looking at an item that's subject to a mode effect and comparing that with factors, trying to get the association between that and factors that are related to the mode that someone uses. So this is mode selection. So to give an example again, imagine that males were more likely to use a telephone survey, but in the telephone survey, you're more likely to say that you're in better health than you actually are. Then it would appear that males are in better health than females entirely spuriously, if there was no association in reality, or if there is an association, it would certainly bias that association just looking at the data as it is. Now, later in this webinar, we're going to talk a bit more in detail about these types of biases and make it formal and show you how to utilize different frameworks for understanding how bias can crop up in your analysis of mixed mode data. The Centre for Longitudinal Studies is home to multiple national longitudinal cohort studies. There's a 1958 birth cohort study, the 1970 birth cohort study, Next Steps, and the Millennium cohort study. Each of these collects data on an array of information across people's lives, but they have each used mixed mode designs in some parts of the studies. So to help users of CLS's surveys, we've created some guidance that's now available online for how to handle mode effects. This guidance is quite exhaustive and detailed. It's got 6 different sections that I've outlined here. It is quite long, but we've written it in such a way that each of the sections is standalone. But nevertheless, because this is a short webinar, we don't want to overload you with information. We're going to try and focus on the key takeaways of the guidance in this webinar, and you can refer back to it later if you want more detail. So the outline of this webinar is that I'm going to start by giving a further background on mode effects. Then Georgia is going to talk about how you can conceptualize mode effects using directed acyclic graphs, which is a graphical way of conceptualizing bias in data. Then Richard's going to talk about some methods that you can use to handle mode effects to try and avoid the bias that might crop up when using mixed mode data. We're going to end with, I'm going to end with some recommendations that we have for when you're using our mixed mode data, and we'll also have a Q&A after that. If you do have any questions, please put them in the chat box, and perhaps while I'm speaking, if Richard and Georgia can just tell me if any crop up, because I won't be able to see them myself. Okay, so some further background. So as I say, we're not going to go through every single piece of information from the guidance. We're just going to try and focus on some key takeaways. So there's many mixed mode elements within CLS's cohorts. The first thing to note is that each study has had some mixed mode elements. Usually selection into mode is non-random. So there's some element of the people who answer in different modes will be different between those modes. So in the sequential mixed mode design, people that respond to the survey later are more likely to appear in later modes, and they will differ from people who respond to the survey immediately. There's mixed mode elements in the main stage, sort of general surveys that people use, but there's also sub-studies within each of the cohorts that might have mixed mode elements too. So, for instance, MCS has data from older siblings. You might want to perform an analysis of comparing MCS cohort members and their sibling, but the data on those individuals might be collected from different mediums. So I think the older sibling questionnaire is paper and pencil, but you might have some web survey face-to-face elements in the actual cohort member interviews themselves. There's between person mixing of modes. By this I mean within a given survey sweep, then people might be allocated to different modes. There's also within person mixing of modes because there are different modes used between different sweeps. And one nice feature of the cohorts, CLS's cohorts, is that you can use them to perform cross-cohort analyses, but this mixing of modes also means that when you combine the data, there might be mixing of modes between studies too. Just to go back to point 2, I just want to say that age 55 of the NCDS actually embedded a mixed mode experiment that you might want to read up more on. So here's just an example of mode switching in next steps. So in wave 4, it was face-to-face only, but then from waves 5 to 9, it was a sequential mixed mode design, web, then telephone, then face-to-face. You can see that within a mode, I hope you can see my cursor, there's people use different modes, but also between modes people switch to some extent. So this blue band here is people that used web in wave 5 and then telephone in wave 4. And as I mentioned, this can cause bias for descriptive, longitudinal and correlational analyses. So what is it about a survey item that might mean it generates a mode effect? Well, Joe Dardenne at NatSen has a nice paper that's highlights 3 overlapping factors. So one is interviewer effects. The presence of an interviewer can affect how people respond. The main way this is that people might be less willing to reveal socially sensitive information when they have to report it to the interviewer. Second is satisficing. So people usually don't put the maximum amount of effort into responding to a survey item to give as accurate an answer as possible. They might do enough just to give a reasonably suitable answer. Motivation might differ between modes. This again is related to interview effects. If there's an interviewer there, they might be more motivated than if they're just doing an anonymous web questionnaire. And also there might be the availability of explanatory information that help people answer a question properly. And again, an interviewer can help with that by explaining questions. Then there's finally a question and answer presentation. So this is how the item appears to the respondent. So the main difference is in telephone and face-to-face interviews, you hear the question, whereas in web, you read the question. In web, you might not actually read to the end of the question or the end of the response categories, and so choose one of the earlier response categories, whereas at the end, in the telephone and face-to-face, you might be more likely to remember the categories that you heard last, because those were the ones that you heard most recently. There's also examples of question and answer presentation being important, where you have the same response scale used across multiple items, where you might just select the same response each time without thinking too much about it. One thing to note, though, is that mixed mode surveys are often designed with these considerations in mind, so that survey managers and designers actively try to reduce mode effects because of the bias that it can cause. So some considerations about this. So one is that mode effects might be contextual rather than something to do with the item itself. If you think about web surveys, you can answer those at any time of the day in any location. So you might be more distracted than in a face-to-face interview where you're at home and you've taken the time out of your day explicitly to speak to an interviewer. It might not just change the mean level of responses, but the whole distribution. So this recency and primacy effect that I was sort of mentioning before might mean that responses cluster at the first categories of an item or the latter categories of an item. It's not just how you respond to an item, but whether you even choose to respond to an item. For instance, in an anonymous setting, you might be unwilling to say information that's very personal to yourself. these different factors that can lead to mode effects might be operating simultaneously, and so that can mean it's quite difficult a priori to predict the direction or the size of the mode effect. And lastly, not all items might be subject to mode effects because they might be very objective, require very little effort on the part of the respondent to answer accurately, and they might be not socially controversial at all. So just to go back to the self-rated health item from before, we had the anonymity might push you towards understating your poor health in the telephone survey, but in the telephone survey you also hear this question, so you might be more likely to report poor health because that's the category that you hear last. So you've got two potential effects that operate in opposition to one another, so it's difficult to know a priori which direction mode effects might occur, and so this is why you might need empirical evidence to decide what will actually happen in practice. Here's another survey question, which is, do you have any children? The question gives very explicit criteria for what is the expected child to be defined as. It's a yes/no question. You can imagine some edge cases where someone might want to give inaccurate information in a particular mode. For instance, if they live with someone that they don't want to know that they have a child, but obviously that's a very rare circumstance. So you'd imagine very little risk of mode effects for an item such as this. Now, as I mentioned, it's worth having this empirical evidence because it's unclear how to predict a priori what a mode effect might be. It's also the case that the size of bias is related to how strong mode effects are and also how strong mode selection is. So in the guidance, we review papers from a handful of major surveys that have looked at mode effects experimentally. We draw a number of conclusions. Firstly, that there's not mode effects in every survey item, as I sort of intimated at before. This is quite useful because you can use some survey items as negative controls. They should only, any difference between mode on those survey items should purely reflect mode selection. Another finding from this review was that social desirability appears to be the main driver of mode effects more than the other factors outlined in the Dardenne report. In any case, though, the actual mode effects when looking at sample means between modes are usually relatively small, about 0.3 standard deviations or lower. And there's also some evidence of recency and primacy effects too, but these aren't as strong as social desirability on the main. We are currently conducting a larger systematic review, which I'll talk about a bit later if I have time to. Mode selection. So we also do some empirical work just to look at the factors that are related to selection into mode in suites 5 to 8 of Next Steps and in age 55 of NCDS. NCDS at that age used a telephone then web design. Broadly, the factors that were related to responding to later offered modes were similar to those that you'd expect for non-response in general. So things that predict non-response, such as lower cognitive ability, more disadvantaged socioeconomic status and poor health, also predict late response to the survey, which in a sequential mixed mode design is directly related to which mode that you end up using. However, trying to control for these factors doesn't seem to be able to fully account for mode selection. So I just referred to negative controls before and how they can be used to look at mode selection. The idea is to control for some of these factors that are related to selection into mode to see if you can reduce that mode selection effect in the negative control to zero, and it doesn't seem to be that you can do that easily. Richard might just discuss that a bit more in a while. Some final considerations are that the selection depends on the particulars of the survey design. You'll need to read the technical reports to understand how people end up being allocated to modes. In the sequential mixed mode design, it's that you responded later to the survey that you end up in a later mode, but also a subset of people might be directly allocated to a particular mode, usually based on the information they have about a person. So someone that the survey managers don't have a telephone number for can't be part of the telephone interview. Mode effects might be heterogeneous according to population. So As I mentioned, social desirability seems to be a very strong driver of mode effects, and what is socially desirable differs across groups. Mode effects can also differ on the survey design particulars. So here, there's some cases where in a web survey, you're only allowed to answer that by particular devices. So you might not be able to do that at certain times of the day or in certain settings, for instance, on your phone. And then the extent of bias depends on what analysis you are trying to do, but also on the strength of mode effects and mode selection. Okay, over to Georgia.
I'm going to be talking about how we can conceptualize mode effects using DAGs and to help us understand some of these challenges and the biases that might be operating a bit more. And I will first start by briefly introducing DAGs generally and what they're used for. So DAGs is short for directed acyclic graphs, and these are generally graphical representations of causal relationships between variables. And the reason we use them is to encode our assumption about the underlying processes and relationships that lead to the observed data and distributions that we see. And in general, we represent variables of interest or related variables using what we call nodes, and then the relationships between variables, so the arcs you see on the left, or arrows are called arcs, or in some literature, edges. And if we see a DAG, we can also sort of read it or interpret it. For example, we can make statements such as, in this case, both U and M are causes of Y because they're linked using these arcs. And we can also make statements such as, for example, if we were to intervene on Y or change Y in some way, then the probability or expectations of Y, sorry, on U, if we intervene on U, then the probability or expectations of Y will change. So essentially, we're talking about probabilistic relationships here. And DAGs have certain key features. So in their name, you see that they're directed and acyclic. So what this means, first, directed means that the relationships that are represented by the arcs are directed. They're directed over time because causality is also directed over time. So we cannot have bidirectional relationships in DAGs. Acyclic means that if we're to start from a variable like U and then follow the path, we can never arrive back at the same variable, so we cannot do a full cycle. And non-parametric means that the presence or absence of an arc can tell us whether there is any probabilistic relationship between the two, but it doesn't tell us anything about the size or strength of that relationship or the specific shape, for example. It doesn't tell us whether that's linear or non-linear. So that's why that's a non-parametric. And the main reason why we use DAGs is that once we've put all of the variables and relationships in this graphical form, we can then identify, for example, which variables are confounders, which variables are mediators, and so on. There are many different variable roles and paths that exist. And this is because a variable role, for example, something can be a confounder only with respect to a specific exposure outcome relationship. And we do this to then try and inform our analysis, for example, to identify what variables to condition on or what variables we might want to avoid conditioning on. For example, usually we would want to avoid conditioning on mediators. And I'm not going to go into much more detail on all the different types of variable roles. I'm going to focus on two specific roles and related sources of bias in DAGs that will be relevant to this part of the talk. So first on the left, we'll consider confounding. And confounding is generally well understood, and hopefully most of you here will have heard of this. But suppose we have two variables, we can call them X and Y, or any exposure and outcome that you might be interested in. And suppose that these are both caused by a third variable, C, or our confounder. Now, these X and Y will now share a relationship that might be spurious just because they have a common cause. And this relationship might not be real, so we call this confounding. But if we were to condition on C, and by conditioning we mean, for example, estimating the relationship between X and Y within strata of C, or within a specific level of C, or including C as covariate in a statistical model, we would then remove this confounding and the confounding bias. On the right, we'll have collider bias, and this of the two is probably not understood as well or as commonly. So suppose we have the same two variables that you may be interested in, but this time they both simultaneously cause a third variable, Z. And it's called a collider because you can think of these arcs as colliding into the third variable. So if you were to just have this scenario, if you were to just observe it, there would be no spurious association taking place. However, what would happen here is if we were to naively condition on Z, we would then introduce a dependency between the two variables that cause Z. And this would be a spurious association, and we introduce collider bias. So it kind of works in the opposite way. When we condition, rather than removing bias, we introduce bias. And if you want to learn more about DAGs in general, because we don't have so much time to go through everything, there are so many resources now out there. They're very friendly and accessible papers, as well as courses and videos that are free. And the thing about DAGs is that, as I said, they're most often used in applied research to try and guide analyses and adjustments, but they're also extremely useful for understanding methodological challenges and explaining them in like an easy graphical way. For example, one of the most important things that DAGs have helped explain or understand is the so-called birth weight paradox, where smoking appears protective in low birth weight babies compared to non-smoking. And actually, this is one of the classic examples of collider bias. And there are many other things that DAGs have helped explain methodologically. And that's why we believe it's really useful to also look at mode effects and the different implications using DAGs. And I'm going to start with just a very simple scenario where we only look at the measurement of a single variable. So suppose we have a node or variable M that represents survey mode. Now, typically this would be binary. For example, we can have maybe web and telephone modes. We also have some variable of interest that we would like to measure, for example, alcohol intake. And of course, we don't know the true value of the variable. We're only able to measure it to a certain extent. So we normally call this latent and depict it using a circle or ellipse to show that it's latent and we don't have a measure for it. And then, of course, we also have the measured version of this variable, the measured alcohol intake, which we call Y star. Now, in this example, we can see using this DAG that M or mode will be a source of variation or error in the measured version of Y, so in Y star. But if we were to condition on M, we can remove this variation in the measured variable that is due to differences in survey mode. And this is quite straightforward. You know, Y star conditional on M is Y in this example. And this might probably make it seem like simply conditioning on mode would be the generic solution when we suspect that we have a mode effect. But of course, the reality is a lot more complex. And so I'm going to go through a few more examples to see when that might or might not be appropriate. So now moving on from measuring a single variable to considering a relationship between an exposure and an outcome. And most of the time, I would be interested in estimating some sort of relationship. So we can stick to the same example of alcohol. You can have something else in mind that you would be interested in. And just for illustrative purposes, we can consider having an exposure, for example, age. And we want to estimate the effect of age on alcohol intake. and alcohol is subject to a mode effect. And throughout, we're going to look at two types of plots where we look at the relationship between X and Y. And on the left, we have the relationship between X and Y, where Y is the true underlying value of Y. Of course, in practice, we would never have this. We would only have the measured version of Y or Y star, but we can use data simulations to demonstrate the general points. And then on the right, we have the same relationship, so regression, where X is the exposure, and this time Y star, the measured Y, is the outcome. So if we were to look at the regression lines, we'll see that we would estimate the same relationship in this case, regardless of whether we have the true or the measured Y. And if we were to condition on mode, for example, if we were to look within strata of mode, we would see that the relationship, again, will be the same. But we would know that we would likely be reducing some of the variation that is due to mode, and therefore hopefully increase our precision. Now consider, rather than an outcome mode effect, an exposure mode effect. So again, we can stick to the example of alcohol intake, but this time this is the exposure, and we have another variable that would be the outcome, for example, self-reported history of a heart attack, just illustratively. Now here, if we're to consider the same sort of comparison and look at the regression lines, we would see that before we do any adjustments, so just the relationships between the effect of Y and Z, we would see that the regression lines look slightly different. Now this is because the variation in the measured version of alcohol that we have, that is introduced by survey mode, would dilute the part of the measured variable that is due to the underlying value of alcohol. So we're kind of diluting the measure of the exposure. This in turn translates to diluting the effect we are measuring. And so what we observe is actually called regression dilution. And it's dilution because you can see the line is kind of turning slightly towards being flatter. So we see a diluted or weaker effect. However, if we were to condition on mode, for example, by looking within strata of mode, we can see that actually we estimate the correct relationship was conditioned on mode, and this would be the same as if we had the underlying true value of alcohol intake. You might be thinking, what if we have both exposure and outcome mode effect? So here we have both the exposure X and outcome Y, having measured versions where variation is introduced due to using different modes. The exact same concepts would apply. So adjustment for mode would help reduce error that's introduced by an outcome mode effect, and would reduce bias or the regression dilution introduced by the exposure mode effect. However, of course, things cannot be as simple as that. And so far, we've only considered mode as sort of this exogenous source of variation in a variable. So we know that the way that the variable is measured might be slightly different depending on the mode, but otherwise we've assumed that the mode of data collection is not related to anything else in the causal process, so to speak. In reality, of course, this is unlikely to be the case. Usually in the health and social sciences, things are very complex, related in a very complex way. And it actually often might be more plausible to assume that the availability or offer of one mode or another might affect selection of different people into the study. For example, given two different modes, we might expect often that different proportions of people with different characteristics would essentially end up responding using different modes. But for example, if someone is not an internet user, then we will not have people with this characteristic if in the web mode. But also, certain relevant variables of interest, mainly we're talking about the exposure and the outcome here, might affect selection into a mode themselves. So let's look at how we would depict this in a DAG. So suppose this time, forget about the measurement element just for a moment, and consider two examples. Very illustratively, again, we can have an exposure like occupation, and then an outcome such as traumatic brain injury. And we can assume that in both cases, there will be some sort of process where both of these, whether whether the effect is smaller or larger, would be probabilistically related to selection into a specific mode. So this time we have args coming out of the underlying variables. And sometimes the easiest way to understand things is if we were to assume that actually this relationship that we're interested in, actually is null. So there's no effect of the exposure and the outcome. And this is because when we look at, the analysis or plots, if we see an effect, then it will be much more easy to understand that this is due to bias rather than a real effect taking place. And indeed, if we simply looked at the relationship between X and Y and compare between the underlying X and Y and then the measures that we've got of the exposure and the outcome, we see that we actually estimate the same relationship, which in both cases is a flat line. So there's no relationship between these two. But what if we were to maybe naively adjust for modoids because we know that this can reduce some of the variation in the measures that is due to mode. So we want to improve our analysis and we condition on mode. We look within strata of mode in this case. What would happen is within each mode, we would actually observe a relationship between the exposure and the outcome, even though in this case, there was absolutely no relationship between them. So here in this data, we've simulated the relationship between them to be 0. And the reason this happens is because hopefully now you would recognize this collider structure. We have two variables that collide in a third one. In this case, this is the survey mode. So conditioning on mode would create this spurious relationship or dependency between X and Y. So this is really important to try and think about anytime you might consider conditioning on mode. And of course, in many settings, both mode effects in terms of measurement and also selection into mode would appear together. The way we would depict this is we would have X and Y, our exposure and outcome, for example, some sort of depression measure or score and alcohol intake, would both be related to selection into a specific mode. And then the mode itself, in turn, would introduce variation in how these variables were measured, depending on the mode used. So we kind of have this happening before and after the mode selection takes place. And again, we start with this assumption that actually, and the data that we've simulated, that there's no relationship between the two in reality, just as an illustrative example. And what we would see in this case, where both of these, both mode effects and mode selection are taking place, is that actually before we've even done any adjustment, we can see that the regression lines are slightly different. So on the left, we have the true values of X and Y. As expected, there is no relationship, but we see a relationship between them on the right where we use their measured versions. And this is because in this case, survey mode introduces variation in both of them, so we can kind of see this almost as a confounding structure. We know that there's that this is related to mode, and to resolve this, we, for example, might decide to adjust for mode in the model or look within strata of mode. And what would happen then is within mode, we would again see a relationship that is not true, because we know, because we've simulated data, we know that in reality there should be no relationship. And again, this is because we have collider bias. And what you might notice here is that if you don't adjust, you have bias in one direction. If you do adjust, you have bias in the other direction. So it's kind of a situation that you cannot really solve just by thinking about adjustment. And also what's important to remember is that collider bias can sometimes be so strong that it can be much larger and can overwhelm any benefit you might get from just reducing the variation in the measured variables. So if you now know about collider bias, you might think, okay, I need both of these to be related to mode so that I have this collider structure where they both collide into mode. But what if in my example, only one of them is related to mode? Am I safe in a case like this where, we assume that fruit and vegetable consumption on its own will be sort of unrelated to the choice or selection of a certain mode? If you have a scenario like this, it might be a trap because it takes just one other variable that maybe we don't know about, or maybe we haven't measured, or maybe we even have measured, but we might not have measured it very well, especially if it's sort of a concept that is very difficult to measure directly, and therefore, even if we adjust for it, this adjustment will not be perfect. If we have any variable that's causally related to the outcome and mode, then conditioning on mode would again introduce collider bias because the exposure and the outcome would again have a spurious relationship that is transmitted from via U. So this is probably one of the most important things to remember. Of course, these aren't just a few scenarios. There are many other examples that might exist. For example, you can have repeated measures in the longitudinal setting, or you might have a mediation analysis. The principles generally extend, and then the user guide that Leah mentioned contains a lot more explanations of these examples as well as other examples. So definitely take a look. And then before I summarize, I'll just mention a few further notes to add to what I've already said. And the first one is that obviously we use some example simulated data to show you just generally what might happen in these scenarios, but whether they're mode effects or mode selection or both, in your specific example, will be entirely context specific. And just because there's no mode effect or selection in a certain example for certain set of variables doesn't mean that this would always generalize. Or if it generalizes, it might not be to every single population. But there might exist some literature to help you guide towards kind of thinking about this, and then that can help you illustrate any assumptions you make about what the data looks like, and therefore help guide your analyses. And similarly, how much bias might be introduced is also very context specific. Both mode effects and selection can be weaker or stronger. So the bias that you would reduce or introduce if you were to condition on mode and you have selection present would be very context specific and often quite difficult to predict exactly how much they will be. So to try and summarize all of this information, there's some key messages for you to sort of distilled for you to take home. And the first one, as I've just said, is that both the presence but also the strength of any mode effect or selection will be very much context dependent. And it's really important to understand the underlying theory. For example, maybe you understand it or you can use some of the existing literature or anything else to help best guide your analysis. And whenever selection into or according to mode, any sort of selection process that's related to mode occurs, we saw how conditioning on mode or statistical adjustment or stratification risks introducing spurious associations from collider bias. And sometimes this can be so strong that it might be larger than any benefit gained from, the reducing the variation in the measured variables. Obviously, where mode effects occur without selection into mode, and we only have this measurement challenge, then it might be appropriate to simply condition on mode to resolve this. But the most important thing that I would like to remember from this section is that this would be an extremely strong assumption to make. So you have to be really confident that both the exposure and the outcome are completely unrelated to mode selection. Because if they are, then this would, if this is quite strong, especially, could even sign reverse the estimates. So whenever you're in doubt and you're not sure, but you suspect there might be some sort of selection process, it's best to assume that selection will be at play, and then consider other alternative methods that don't maybe rely on this assumption that no selection process is taking place in relation to mode. And Richard will be talking about some of these alternative methods to conditioning in this next section.
So if anyone joined late and missed the introductions, my name's Richard Silverwood. I'm an Associate Professor of Statistics and the Chief Statistician at the Centre for Longitudinal Studies. So I'm going to be talking in this section about some potential methods for handling mode effects. So I'll go through these three approaches here. Sorry, that's my door, I'll ignore that. Statistical control, multiple imputation, and sensitivity analysis. So I'll just introduce the ideas briefly, go through some kind of advantages and disadvantages of each, but as has already been flagged by both Liam and Georgia, there's a lot more information in the user guide that's already been linked to in the chat by Richard. So if you want more information or further clarification, I would definitely point you in that direction. I'll then walk through a worked example. Again, this is an example from the user guide, and there's a further worked example there if you're looking for more examples of application of these approaches. So the first method I'm going to look at is statistical control. So if we're interested in obtaining an estimate of association, it might be possible to account for mode effects using control variables. So George has already set out some examples of where this might be possible. If there's no relevant mode selection, this might just be adding an indicator variable for mode to the substantive model, or alternatively stratifying by mode. So we'll look at a few DAGs following this just to see cases where this may or may not be a sensible approach. And so this might just be, if you're interested in an association between an exposure and an outcome, it might be adding the mode variable to your regression model. But instead, sometimes it might be preferable to estimate the mode effect using the data that you have. Use this to predict the counterfactual values for those who are observed in the alternate mode, and then analyzing this kind of adjusted version of your variable that's subject to mode effects. Sorry. So in the cases where there's mode selection according to some variables, so some variables affect the selection into mode, just including your mode variable in your regression model or using just this variable to predict mode effects may not be sufficient, and as George has already said, may in fact increase bias. And I think this is a very important point to emphasize, that just this simple approach of including your mode indicator in your regression model may not be a good idea, and it may in fact make things worse. And if this is the case, when you've got this mode selection, then you would need to include a larger selection of control variables. But it's possible that these control variables may not exist in your data. So for example, you may not even know which factors affect selection to mode, so you haven't measured them. Perhaps you do know what they are, but they've not been measured if it's a secondary analysis of existing data. And it may be that it's not possible to really observe these. For example, if the variable that's subject to mode effects also affects selection into mode, then you're unable to observe the true value of that directly. So let's have a look at a few examples of approaches and think about whether statistical control would be useful here and how exactly we would apply it. So these are similar DAGs to those that Georgia showed. So here we're interested in the association between X and Y, or the effect of X on Y. We can see here that there's no arc going from X to Y. So here there's no causal effect of X on Y. Y here is observed under different modes, and there is a mode effect, which is shown here by the arc going from the mode M to Y star, our error-prone observed value of Y. And so here, if we're interested in estimating our association between X and Y by regressing our observed Y star on X, we will see that instead of observing the null relationship that we can see from the DAG, we should be obtaining, there's a path from X to Y star via M that means that we will not estimate that null association. So in this example here, we could simply control for M by including it in a regression model of Y star on X, and then that would remove that path, and we would get the null association that we know that we should do from this DAG. If instead we wanted to estimate the mode effect, then we could do so here by regressing Y star on M. We could use that to adjust the observed values of Y and then regress that on X, and we should get a similar answer. Here we've just extended this DAG by including a variable U, which is a common cause of M and Y. The setup is the same apart from that. So now if we instead regress our observed Y star on X, and control for just M, this will no longer be sufficient to allow unbiased estimate of the association between X and Y. And that's because M here is a collider, which would mean that when we condition on that, it's opening up an additional path. Instead here, we would need to also condition on U, and we can do that again by including that in a regression model. In practice, U is likely to be more than one variable, and so of course we're relying on being able to observe all of those variables, or at least something that's sufficiently close to all of those to allow us to appropriately control for U in this instance. And this third example here extends the first example by allowing Y, our variable that's subject to a mode effect, to also impact on or affect the mode that's been used in the data collection. So here, this is particularly problematic because it means that if we regress Y on X and try to control for M, then again, this is a collider, so we'll introduce some spurious association. If we don't control for M, then again, we're going to have bias because of the mode effects. So this is a particularly problematic situation where controlling for M or not doesn't help. So the statistical control approach is particularly straightforward, it's easily understood and implemented. And if we're trying to account for the selection into mode, then the sort of studies that we're talking about here, the cohort studies that CLS runs, have particularly rich variables going back many years, many of which are likely to be to impact on the selection of mode. Excuse me. So we may be in a good situation where we can control for mode appropriately. However, there's some strong assumptions here that we're accounting for, that it's very difficult to ensure that we've correctly accounted for selection into mode. The control variables that we need to do this may be, as I said, unknown, potentially unmeasured, or just poorly measured. And if that's the case, then bias may persist. And a final point here is that when we include these variables in our regression model, then that can affect the interpretation of the model itself. So we're then making conditional interpretation, and that might not be what we want to do. And that's the sort of setting in which you might want to predict the mode effect and use that to adjust the value that you have of your variables subject to mode effects. Okay, the second approach that I want to look at is using multiple imputation. So people might be familiar with this approach because it's something that's increasingly being used in the handling of missing data. So in this approach, what we would do, we would take the values of the variable that's hypothesized to exhibit mode effects, and then artificially set them to missing for individuals who are in the alternate survey modes. So here you can see immediately that we're throwing away, getting rid of potential information that we have in our data collection, which might not be a desirable property of the approach. We then use information that we have on individuals who were observed in the reference survey mode and develop predictive models. And we then apply those to the data that we have for individuals in the alternate survey modes to generate the counterfactuals, so the values of the variables subject to mode effects that we would have observed had we observed those individuals in the reference mode. We've then obtained completed data sets, so we've refilled those missing values in our data sets. And we can use these in analyses in the usual way to provide descriptive statistics or analyze them in substantive models. So that description so far is a kind of single imputation approach. And perhaps you can see that if we were doing that, then there's some uncertainty inherent in the imputation process that we're not accounting for. We really should be propagating that uncertainty through, and that's where multiple imputation comes in. So here we impute multiple data sets using a similar procedure. In each of those data sets, we analyze these completed data using the substantive model that we're interested in, and then we pool these estimates across imputed data sets using standard rules that allow us to obtain standard errors that account for uncertainty, as I say, inherent in the imputation process. So if you're familiar with multiple imputation for dealing with missing data, then perhaps this all sounds very straightforward. You can see we're just artificially creating the missingness and filling it in a very standard way. But let's have a look step by step in case this is less clear to anyone. So let's take a concrete example. We've got a battery of 5 mental health questions here. So in the data set below, these are MHQ1 to MHQ5. They were asked by 2 different modes: telephone, where we're using an interviewer, and web, which is anonymous. And what we're really interested in here is the sum score across these 5 mental health questions. So the final column just sums them. So we'll get rid of the individual question responses, so we can see a bit more clearly what's going on. So in the multiple imputation approach, as I say, the values of the sum score would be artificially set to missing for telephone respondents. So here, because web is an anonymous mode, we're wanting to use that as our reference mode. And then we're going to think about what would happen if we'd instead observe those participants who responded by telephone instead by web. So after setting those to missing, we then develop an imputation model for the sum score among the web respondents. So those here highlighted in blue. So we develop a model that will allow us to impute the values of the sum score. We then go ahead and do that. So for those individuals responding by telephone, they now have an imputed value of the sum score. And this is the counterfactual. This is what, conditional on the variables here that we've included in our imputation model, we would expect to have observed for those individuals had they instead completed the survey by web. And so that gives us a single imputed data set. We would repeat that process to create multiple imputed data sets and analyze them. So as I say, conduct your substantive analysis within each of those imputed data sets, combine them across data sets using standard rules to allow us to appropriately propagate the uncertainty. And we're going to walk through an example application after this. So if it's still not completely clear, then hopefully a bit more so by then. So there are some advantages of this approach. As I say, it's increasingly commonly used for handling missing data, so it might be familiar to researchers already. There's easy to use and thoroughly documented functionality in all the major statistical programming languages. It's straightforward to implement for a wide variety of variable types, which is important. So here we were thinking of imputing a variable here, sorry, the sum score that looks basically continuous. But if we had a variable that was, say, binary, then using standard implementations of multiple imputation, we would be able to develop a predictive model for that binary variable that gives us a probability. But then we would be able to use those probabilities to have in our imputed data sets variables taking the values of 0 and 1 if it's a binary variable, so we know that it's appropriately distributed variable given the potential observed values of the variable. If we're already using multiple imputation for handling missing data, then we can just bundle this use of multiple imputation for also dealing with mode effects into the same procedure. So it's not adding a huge amount more to the process. A potentially major disadvantage is that it doesn't use information from the observed values in the alternate mode. So the first step here was to artificially set those values to 0. This is potentially very wasteful. So obviously this will be a function of the proportion of participants who are participating by the alternate mode. If it's only a small proportion, we're not throwing away much information, it's less of a worry. But also, if only a small proportion of our participants do participate by the alternate modes, then mode effects are unlikely to be a major issue anyway. So perhaps we're less likely to be using this sort of approach in that situation. There's a particularly strong assumption underlying this and any application of multiple imputation, which is that the data are missing at random. So here, missingness is the artificial missingness that we've created, but the assumption says that that's independent of the counterfactual value of y, conditional on all of the other variables that have been used to generate the imputed values. And this is potentially very problematic if we think that the true value of y, the counterfactual value of y, is itself involved in selection into mode. And if that's the case, then we have a missing not at random situation, and multiple imputation will not give us unbiased results. There are extensions to standard sort of MAR assumption multiple imputation that will allow you to look at potential missing not at random mechanisms, often in a kind of sensitivity analysis setting. So there are some extensions that could be useful in that setting, but again, it's adding further complexity. The final method we're going to look at is sensitivity analysis, or quite a specific example of sensitivity analysis here. So sensitivity analysis comes within a broad area of quantitative bias analysis. This can be approached in different ways. So some of these types of bias analyses will take the entire conducted analysis and just focus on that and look at different ways in which that could be impacted on by different biases. Here, what we're doing is an approach where we're making amendments to the record level data set and then using that in sensitivity analysis. In particular, what we're doing is we're making assumptions about the size of the mode effect. We're using that to simulate counterfactual response for those in the alternate survey modes, and then using our substantive model within those simulated data sets. And once we've done that, we compare the results from our simulated data set against exactly what we would have achieved, what we would have obtained, if we'd applied the substantive model using the observed data. Really addressing questions then of whether and to what extent the results change for different assumptions of the mode effects. So how might we go about choosing mode effects to use in sensitivity analyses? So there's three different approaches here. Perhaps there's more, but these are the ones we wanted to highlight. So the first option is you might choose to use a single plausible value of the mode effect and use this to try and obtain a best estimate of your estimate of choice, so your descriptive statistic or your regression parameter of choice, perhaps. So how would you go about doing that? So there's an existing literature, mainly using experimental data to try and estimate mode effects in different settings. So obviously, as has been described already by Liam in particular, the extent of mode effects might differ depending on the setting that you're using. So the population, the specifics of the question that you're using, the exact modes that are being compared. So it might be difficult to find something that's in the existing literature that exactly matches the setting that you're working in, but hopefully you can find something close to that. If not, there might be the opportunity to analyze some data yourself, either experimental data or observational data externally, or you can try and estimate the mode effect using the data set that you're trying to analyze. Then obviously it has exactly the same caveats that we've already discussed about the problems with trying to estimate mode effects in different settings in the presence of mode selection. Instead, you might not worry too much about exactly what's the single most plausible mode effect in your given situation. You might consider just a fine net of different values of the mode effects. Try all of those, summarize them in some way, often using a graphical approach, and then see if the sensitivity of your findings, whether your findings are particularly sensitive to any of those different mode effects that you're considering. And finally, you may intentionally choose a completely implausible mode effect. So you might think that there's a range of plausible mode effects, choose something even beyond that, with the idea being then that if your substantive conclusions don't change even in the presence of an implausibly large mode effect, say, then they're certainly not going to change for mode effects within a more plausible range. Okay, so a quick example looking at sensitivity analysis application. The same data that we were using before, using the battery of mental health questions. Again, we're just focusing on using the sum score of these. So we may go away, look at the existing literature, and find that the best estimate of a plausible mode effect for the sum score in this situation, so this specific between mode comparison, this type of a population, is +1 unit when we're comparing telephone data collection with web data collection. So in our sensitivity analysis, we would just go from our observed sum data here to this final column of data where we're reducing by 1 unit the sum scores for telephone participants. This will give us our counterfactual values for web respondents for the value of the mode effect that we're assuming here. Then just use these values in a substantive analyses, and this would provide us with a best estimate of our chosen descriptive or analytic parameters. But it might be that we are unable or perhaps unwilling, because we don't believe that the values in the literature will transport to our given situation. We may not want to believe that that value of +1 unit is really going to give us something that's a reliable best estimate. So instead, we might use a fine net of mode effects. So here we're using a net of values between 0 units, which would be no mode effect, going up in values of 0.1 up to 2 units, which would be very large mode effect. So here we use these values in the same way, generate these new simulated variables, which are the counterfactual values for everyone under the same mode of data collection. Again, conduct our analysis of choice, display these perhaps in some graphical way, and see how sensitive our conclusions would be. And as I said, the final option might be to choose an implausible mode effect. So here, say 5 units, go through exactly the same process. The idea being that if substantive conclusions don't change, even with an implausible mode effect, then they shouldn't do for a more plausible value. So advantages of this approach: mode effects are assumed rather than estimated, so we don't require a detailed understanding of mode selection. Unlike multiple imputation, where we said a major disadvantage was potentially throwing away a large amount of information, we're not doing that here. We're just making adjustments. So it seems preferable from that perspective, and it's extremely flexible. There's lots of different ways that we can use this approach. So for example, if we believe that there's heterogeneity in mode effects, so different mode effects for different population subgroups, we can allow different mode effect parameters for each of those. So say we think mode effects are different in men and women, then we just allow them to differ by having different parameters and applying those in our sensitivity analysis. Similarly, if there's multiple variables that are subject to mode effects, either collected at the same sweep of data collection or different sweeps, then we can allow for that in the analysis by having different sensitivity analysis parameters. And again, if we're mixing modes between sweeps, the same thing applies. Disadvantages, if we're really trying to use a plausible estimate of the mode effects and conduct a single analysis, then we might not know what that is for any given situation. But I'm not sure that's a major limitation, because we can just use this fine net approach over a plausible range instead and assess sensitivity that way. If we really want to try and get to that in our own data, then we might be having to estimate the mode effects from non-experimental data with the same concerns as being described already. And then finally, there's no real out-of-the-box functionality in major statistical software for performing really general sensitivity analysis. So it would require a little bit of coding, but I think it's nothing too advanced necessarily. Okay, and then in the last couple of minutes, I'm just going to go quite quickly through this worked example from NCDS Sweep 9. So again, this is provided in more detail in the user guide that's already been linked to. So as a bullet point of background, there's been evidence for across different settings and across time that individuals in more advanced socioeconomic position have better health on average. So we're trying to address this question using NCDS Sweep 9, a cross-sectional analysis, looking at social class as the exposure. So that's just a very simple binary professional versus not variable, and with an outcome of quality of life. So that's captured using the CASP-6 score. So this is the DAG that represents that. I'm just going to quickly go through the justification for these different arcs that have or haven't been included here. So within NCDS Sweep 9, there's an experimental sub-study, and analyzing the data there, we can see that there's evidence of a mode effect on the CASP-6 score of about 0.25 standard deviations comparing telephone to web. So that red highlighted arc is there, and that's positive because a telephone mode is associated with a higher CASP-6 score. There's no evidence of mode effects in reporting social class, which is why we don't have a separate counterfactual and observed social class node here. There's evidence that professional social class is strongly related to web participation. So this is the red highlighted arc here. So a higher social class makes you less likely to have participated by telephone mode. So that's a negative direction to that arc. Excuse me. And there is also evidence that higher quality of life is related to higher level of web participation at age 55. So that's the red highlighted arc there that would have a negative sign. So this is a situation that we've already looked at before, really. So a simple regression of the observed CASP-6 score on social class will pick up both the true positive association between social class and quality of life, highlighted by the combination of red paths here, but also this negative association due to the mode effect. And so we would, the estimated effect would be underestimated or understated. So this is the selection of different analyses we've conducted to try and address this. I'll go through each of them in turn. So the first one is just the naive estimate. So it's a simple regression of the CASP-6 score on social class. As we say, this is likely, given the assumed causal structure, to be an underestimate of the true association or the true effect here. But we estimate that individuals in the professional social class report a 1.2 points higher CASP-6 score on average, so have a higher quality of life. So the next thing that we do is try including just an indicator variable for survey mode. So I'll just pop back to the DAG. So what happens when we do this? We can see that survey mode here is a collider. So we believe that by doing that, we would also really need to be adjusting for the confounders here. And there's a problem also because it will induce some association with the counterfactual value of the CASP-6 score. So we would expect that adjusting for, accounting for mode by itself isn't going to be sufficient to address the mode effects here. But if we do that, we see a slight increase in the size of the association to 1.24. But as I say, it's likely to be biased. We instead use a multiple imputation approach. We get an estimate of 1.14, but we would suggest again that this is likely to be biased here. So mode selection, because there's mode selection according to the quality of life, it means that the CASP-6 score for the web participants are missing not at random. So wouldn't meet the missing at random assumption underlying the multiple imputation approach. If we extend our statistical control approach to include several measures related to mode selection, we get an estimate of 1.28. But here, as we've been saying throughout, it's difficult to ensure that these set of control variables will fully capture mode selection. So there may be residual bias here. The next two results here relate to instrumental variable regression that I've not had a chance to discuss today. So I'm going to skip over those, but more information on that in the user guide. The final set of results here are those from the sensitivity analysis. So here we've used values for the mode effect between 0 and 1 standard deviation, though effects over 0.5 standard deviations really seem to be implausible given the previous literature. But what we see here, which perhaps is easier if I get rid of the box, is that for all of these different values of the standard deviation, of the mode effect, as the mode effect is increasing, these are actually moving further away from the null. So certainly wouldn't change the substantive conclusions that we're drawing. And we would say even for an implausibly high mode effect of 1 standard deviation, it only increases the estimated association by 36%. Substantive conclusion remains the same. Individuals in the professional social class have higher quality of life. And so we would suggest that by using this sort of sensitivity analysis approach, it's allowing us to do something more concrete than just having a sort of a statement in your discussion section that's saying, well, mode effects might be a problem. We can do something a bit more about it to explore that sensitivity. And I will pass back to Liam. Thank you.
Thank you, Richard. Just one thing to mention as well, just following on from what Richard said, is that you can get annoying comments from reviewers that would be there's some potential for mode effects there, where with sensitivity analysis, you're able to put numbers on that that critique that the reviewers had and focus the disagreement. So what is a reasonable and plausible mode effect to assume, and does that, if you use that, does that affect your conclusions? Even if you use an implausible one, does that affect your conclusions, rather than have some hypothetical situation that doesn't really resolve the disagreement whatsoever and doesn't take you any further. So I've not moved my slides much further on, so I'm just going to skip through. So I was going to finish. I just realized the time is coming towards the end. I don't want to eat into the quick Q&A time too much. The guidance document has a list of recommendations. There's a lot of slides here. Okay, there we go. So we've added some recommendations on how to handle mode effects when you're using our cohorts. This sort of involves the steps that we've discussed here. Draw out your assumptions using a DAG, have a sense of what the likely size of mode effects will be and what variables would suffer from mode effects and where the bias might be as a result. Report statistics, descriptive statistics by modes, have a sense of mode selection, and then try to run sensitivity and other analyses that do account for mode effects or attempt to account for mode effects. I just want to finish before the Q&A with a few more points. So Richard, Georgia and I currently work on a Survey Futures ESRC project looking at mode effects in practice. This discussion today has been quite hypothetical. So what we're trying to do is make mode effects problems grounded in empirical evidence a bit more. So one element of this is to perform a systematic review of experimental mode effect estimates so that people can incorporate these into their sensitivity analyses, so you can have plausible assumptions when you're performing sensitivity analyses. Another one is a tutorial on how to actually perform these sensitivity analyses, because they can be quite complex and the coding can be somewhat difficult if you're not that experienced with coding. But another is sort of answering the questions of which methods work in practice and are mode effects actually sufficient to change results in real world data. So one analysis we're going to do is to use negative controls to look at whether statistical control can account for mode selection sufficiently to reduce any mode differences in those negative controls to zero. Because if you can reliably use statistical control, then that's an easy method for people to use. Then there's another study where we're going to look at in mixed mode data, are mode effects ever sufficient to change your substantive conclusions? So this would be running a series of analyses, assuming that mode effects don't exist, and then performing sensitivity analyses that account for mode effects properly, and seeing whether there's any qualitative or quantitative difference in the results. So hopefully that'll give a bit more empirical evidence on whether these problems actually matter in real world practice.